Hello everyone, welcome to the next lecture of EC573 Advanced Embedded Logic Design Winter 2022 semester. So in the previous few lectures, we discussed about the AXI protocol, we discussed about the AXI memory map protocol. In the AXI memory map protocol, we discussed about the read and the write transaction. Then in the read transaction, we discuss about the address and control channel and data channel. And in the write one, we discuss about the address and control, data and the response channel. Then we discuss about the signals in this channel. We discuss mainly about the valid, ready, then information signal. Then we discuss about the last signal, and then we also discuss about the AX size signal, AX ID signal. Then we discuss about the AX length signal, and we also discuss about the burst type, which is the increment, fix, and the ramp. In the last video, we discussed about the increment type of burst, INCR. And now in this today's lecture, we will discuss about the wrap burst. So in the wrap burst, there is a one important thing which you need to keep a track of, which is the wrap boundary. So the wrap boundary is the size of each transfer in the burst multiplied by the total number of transfers in the burst. For example, if you have a burst length of 4, and the AX size is again 4 bytes. So that means your wrap boundary will happen at every 16 bytes. Okay. So again, same example, AX length is 3, that means burst length is 4, AX size is 2, that is 4 bytes per transfer. You will have the wrap boundary at every 16th address. Okay, this is called as a wrap boundary. Why this is important? Because in the wrap protocol, you will start at the starting address. Suppose this is your slave, you will start at this starting address. Then you will reach to some higher address. Okay. Sorry, I'll just need to redraw this one. Okay. So this is your slave. Okay. So in the slave, suppose this is your starting address. So what you are going to do, you are going to start writing up. You will reach certain boundary. After you reach certain higher address, I can say as a higher address or upper maximum address. After you reach, you will come back to the closest possible boundary, which is the wrap boundary. Okay. So, and then you will keep on starting writing like this. So the wrap boundary is the point where you will return after you reach the certain higher address. Okay. This higher address, I can call it as a again a next wrap boundary. Okay. So you will understand this in more clearly in the next couple of slides. But I can see that once you start from the start address, you will reach, once you reach towards the next immediate wrap boundary, you will go back to the previous wrap boundary. Okay, this is what the concept of the wrap boundary. So when the burst reaches the wrap boundary address plus the number of bytes times the burst length, because you can see that this is indicate the complete wrap boundary, right? In this case, this is the same thing here. When your address reaches the wrap boundary address plus this another the size of the boundary, it wraps back to the wrap boundary. So the same thing which I mentioned here. Suppose that these are your total wrap boundaries. So all these are indicate your wrap boundaries. Okay. Suppose this is your starting address. Once you reach towards the next wrap boundary, which will be the current wrap boundary plus the number of bytes in this transfer into the burst length, that is the same as the wrap boundary. Then you will go back to the lower wrap boundary and start writing like this. So for example, take the example of the your total burst. In a burst, you are writing the 16 bytes of data. Then your wrap boundaries are this one, this one, this one, this one, this one, this one. Okay, these are your wrap boundary. Now suppose that you start your master sends the start address as a say 20, and you are going to write 16 bytes, so you will write the 4 bytes here. So 4 bytes on this one, then next 4 bytes here, then next 4 bytes here, and next 4 byte here. So it is same as the increment board. Now take the example where the master sends the start address as like this. Okay, in this case you will write the first 4 byte here, then 4 byte here. You have reached the wrap boundary, so you will go back to the lower wrap boundary or previous wrap boundary. You will write the next 4 bytes here and next 4 bytes here. So this is the concept of the wrap boundary. Okay, so for example, let's consider another one where your burst length is 8 and the transfer size in each transfer size each transfer in a burst is 4 bytes. Okay, so in this case you can see that you are going to transfer 32 bytes. So your burst wrap boundaries are this one or this one or this one, or okay, these are the 3 wrap boundaries. Now suppose that your starting address from the master is say this one. Then you are going to write the first 4 byte here. Okay, then you are going to write the here, then you are going to write here, then you are going to write here. Then you reach the wrap boundary, you will come back to your you will come back to your this wrap boundary, the previous wrap boundary. Then you will write it here 5, 6, 7, and 8. Okay, so this is how the wrap concept works. Now let's take the another example. Suppose that your start address is this one. Then what you will write? You will write first here, then next 4 here, 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 then here. Then you reach the wrap boundary, you will come back here, you will write the here 7th one, and that's it. So you have written the, oh sorry, this is the 8th one. So you have written the all the 32 bytes of data. Okay, so this is how the wrap concept works. So in the wrap boundary, you can see that the slave needs to should be able to calculate the appropriate wrap boundary so that it will wrap around correctly. So here let's take the example. Here my starting address is 32 hex 38, and the length is 3, and thus I'm transferring 4 bytes. So total I'm transferring in the burst, I'm transferring 16 bytes of data. So if you go to the previous slide, you can see that in the previous slide my wrap boundaries are like this. Okay, so if you go to the previous one, my wrap boundaries are like this, and my address is 38. So you can see that I'm talking about this one. So these are the 2 wrap boundaries which are important, because I'll write here, then I'll come back here and here. So you can see that this is the right boundaries the slave needs to be calculated. So to allow the slave to be able to calculate this wrap boundaries correctly, what is done in the wrap protocol, AXI wrap mode, the master must make sure that the address is aligned. In case of the increment addresses, the first address may not be aligned, right? Master is not required to send the aligned address. But since in the wrap one, the slave has to calculate the addresses correctly, this address and this one, it is compulsory for the master to make sure that the addresses are aligned. What do you mean by addresses are aligned? In case of the 4x size of 4 bytes, that is 2, that is 4 bytes, the addresses can take only these values 048C, 121418C and so on. Addresses cannot take these values. So this is called as a address aligned. This alignment should be with respect to the AX size. So now this is the one, and we can see that from the previous, the addresses, the wrap boundary is 30. Okay, so it is 0x30, and we should be, a slave should be able to calculate it. Okay, and the upper boundary is 0x30 plus 16, that is 40, as we have discussed in the previous slide. Now to calculate this boundary, this is the equation is there, which you can look at, you can put the numbers and you will get this. So slave uses this equation to find out the wrap boundaries, and the next wrap boundaries will be this wrap boundary plus 16. So slave knows this one. So slave will get the start address. Slave will keep on counting whether it has reached this one. Once it reaches, it will go back to the your wrap boundary. And this is how the slave will do. So given the address, given the AX length and AX size, you should be able to calculate the lower wrap boundaries and the upper wrap boundaries, so that you should be able to know how the from where the slave will start writing, that is from starting address, slave will go up and then it will reach the higher address, which is HA, and it will go back to the wrap boundary, and then it will write the remaining data up to this point. Okay, so you should be able to know how this transfer happens, and then you should be able to find out the start address for every transfer in a burst. For example, in this case, you have the 4 transfer in a burst, so you should be able to know the starting address of the first one, starting address of the second one, starting address of third, and the starting address of fourth. You should be able to calculate. So the wrapping burst is similar to an incrementing burst that we have studied. Only case is that in that the address of each transfer in the burst is a careful increment of the previous transfer address. In a wrapping burst, address wraps around to a lower address when it reaches the higher address or upper wrap boundary. The start address of the burst, that is AXADDR, must be aligned in the wrap one. In case of the increment, this is not required, but in case of the wrap one, master makes sure that the start address is aligned. That is the compulsory, master needs to make sure. And in case of the increment, your burst length can go up to 256, but in case of the wrap, the burst is limited to these 4 values. So your burst length either can be 2, 4, 8, 16. It is a power of 2, and there is a particular reason behind this. We'll discuss it in the next slide. So why there is a need of such a complex burst type? Okay, so this is originated from the embedded system. As we know that in the embedded system, we have the cache memory and we have the main memory. And usually data is communicated frequently between the cache memory and main memory. For example, in the processor usually checks for the data in the cache memory. If the data is not available in the cache memory, processor then fetch the data in the main memory. Now, usually what happens, right? Your cache memory is divided into the blocks of data. So this is called as a cache line. So each block of data is called as a cache line. And in your main memory, in the simplistic one, may also consist of, say, blocks of data, which we can call it as again, we can, for the name easier understanding, we can call it as a cache line. So size of this one is same as the size of this one. So whenever the data is communicated, when transfer between the cache memory and the main memory, It is not just you do the small block of data. Whenever the data is communicated, you completely copy the block of data entirely into the corresponding main memory or vice versa. For example, processor wants the data which is say stored in this cache line, but processor doesn't want the entire data. Processor wants only this data. So when the processor wants this data, not only this data, but entire cache line is copied to the one of the cache line in the cache. Okay, from the main memory to this one. So the transfer of data takes place in the size of the cache line. Now you can see here that now the processor is working. Processor wants this data, and only the data which is this one. Okay, so this is the data which processor wants. But since in the regular mode, in the incremental mode, what will happen? The first, you can see that what will happen, the first, this data will be copied, then this data will be copied, then this data will be copied, then this data will be copied, and so on. So that means processor has to wait till this data is copied before the data needed by the processor is copied into the cache and processor start working on it. That means processor has to wait significant amount of time, because copying the data from the external memory takes a large number of clock cycles. So the processor has to wait, which impacts the overall throughput of the embedded system. So using the RAP1, what happens? Processor tells that this is my important data for the immediate requirement. So processor will give the start address like this. So the data will be copied from like this. So the data which is required by the processor is first copied into the cache line. So the processor is free to start its operation. And then the rest of the data, which is this one and this one, is copied into the corresponding cache memory. Okay, so this is where the RAP feature in the AXI is important. So it reads in a cache line with a critical word first. So whatever the data required by the processor on the immediate basis, it is copied one. Then the rest of the data in the cache line is copied. Okay, so this is the same thing, that suppose this is your entire cache line. Then the critical data is copied first. Okay, these are the data which is copied, and then the rest of the data will be copied in the cache memory. And since the cache size is usually small and they are of the power of 2, that's why this is limited to burst length in the RAP1 is limited to these values. Okay, so that is the one where this RAP protocol is useful. Now these are the certain examples. For example, my starting address is 0x04. My burst length is 4, and my each transfer is 4. So total I'm transferring 16 bytes. So I'll have the burst, okay, one burst, and I'll have the 4 transfer. So for the first transfer, my address is 0x04. For the second transfer, what should be my address? For third transfer, what should be my address? And for fourth transfer, what should be my address? Now, in the increment one, the transfer address will be 0x08, 0C, and 08, I think 10, if I'm correct. But in the RAP one, you need to calculate the higher address as well as a lower address, that is RAP boundary, and you will see that it will be 0x04, then 0x08. Then you will reach the lower upper address of the boundary, which is 0x10, and then so you will reach the upper after 0x0C, you will reach this upper address, which is the RAP boundary, and you will come back to lower one. Okay, so this is what how the addresses will be there. So if you want to visualize this, we can go back to our address calculation slide. You can see that here. Here, if you look at this one, my starting address was this one. Then I go here, then I'll come back here. So you should be able to calculate the corresponding addresses. Similarly, here you will be able to you should be able to calculate the addresses. So this will be the addresses. Then for the 8th one, you should be able to calculate it on your own. Okay. So you should be able to calculate the start address for every transfer in a RAP1 given the value. Now let's move to the next signal, which is the ID signal in the AXI memory map one. So in the AXI memory map, there are 4 IDs are there. One in the address write and control, one is the address read and control, then the read data, and then the write response. So you have 4 addresses. You don't have the WID. There is a special reason. You should be able to identify what you should be able to know or judge why there is a no need of WIT after the discussion is complete. So AXI IDs are used as a transaction identifier. That means they are able to identify every transaction that is in the write transaction. If there are multiple write transactions, it is used to ID is used to identify the transaction. It is used by the master and slave to identify the separate transaction that must be written in an order. So you can have the same ID for the multiple transaction. Okay, this is allowed. Okay, so you can have the same ID to the multiple transactions, and you can have the same different ID to the multiple transactions. So how to use this? So by using the ID, master can issue transaction. Okay, master can issue transaction without waiting for earlier transaction to complete. So when the master sends the 2 write transactions, one with the ID 0 and one with the ID 1. So say this is given to the slave 1, this is given to the slave 2. There is a possibility that since slave 2 was free, it will complete this transaction first and then slave 1 completes the transaction. This might be a possibility. But when the master sends the 2 transactions with the same ID 0, then there is a requirement that this should be completed first and then only this should be completed. Okay, so what is the requirement? All the transactions with the given ID must be remain order, but there is no restriction on the ordering of the transaction with the different ID. So use of ID is optional for the AXI protocol, but when they are used, it should be clearly mentioned. So the slave must ensure that now you can see that the if you talk about the read transaction, in the read transaction, what happens? The master sends the read address and control information and the slave to the slave, and then the slave sends the read data to the master. Now, in this case, master will use the ARID on the this transfer to send the read transaction request. Slave will copy that ARID in the RID while sending the data back. So the slave must ensure that the RID value of any return data must matches with the ARID value of the address corresponding. And the same concept we can use for the BID, that the slave must use the same BID for the corresponding AWID. And from this, you should know why there is a no need of the WID. Now, this can get complicated when you don't have the master and slave directly connected to each other, when you have the interconnect between the master and slave. So in this case, interconnect must ensure that the read data from the sequence of transaction with the same ARID value targeting the different slave is received by the master in the order that is issued by the address. For example, this is the master. It sends the 2 transaction, write transaction 1 and the write transaction 2. This goes to this slave and this goes to this slave. Then the slave must send back. The interconnect needs to make sure that while sending back, this should go first and then this should go first, because both were of the same ID. So this should be completed first and then this. This is the requirement in the interconnect. Interconnect must need to take care of it. You may wonder what happens when the 2 masters uses the same ID, because these are the integer numbers. Two master may use the same ID here. So in that case, interconnect assign it in addition to the ID, assign its bits, so that some bits, so that it can distinguish between the different masters. Okay, this is taken care by the interconnect. Now the last signal we are going to discuss is the response signal. Okay, this is the last signal we are going to discuss. Now, if you remember our discussion in the write transaction, your master sends the data address and the control information to the slave. Then the master sends the write data to the slave, and then the slave sends the write response, I can say response, to the master. Okay, and this response signal, in this response signal you have three signals. One is the data, one is the valid, and one is the ready. These are the, we use the B data, B valid, and B ready. So this is nothing but this response signal, and it gives a 2-bit value. It can take OK, exclusive OK, slave error, and the decoding error. Now in the read transaction, you can say that the master sends the address on the read control and the data to the slave. Then the slave sends the read data to the master, and there is no response. But inside this read data, there is a data information signal, valid, ready, it can be last also, and in addition there is a response signal. This is our response, and this response signal is nothing but this one. Okay, so this response signal is a part of the write response channel, and this response signal is a part of the read data channel. Okay, you need to be careful about this one. So for a write transaction, you can see that there is a single response is signal for the entire burst. You don't, in a burst, if you have the multiple transfer, the slave will signal only one response for an entire burst and not for the each data in a transfer. This is in the write transaction, because there is a separate write response channel. In the read transaction, since the read response is a part of the read data, slave can signal different response for every transfer in a burst. For example, in a burst of the 16 read transfer, the slave might return OK for the 15 of those transfer and slave error for the one of the transfer. Because you can see that in case of the read transaction, you have the so suppose this is the AR address, then you have the valid, that is the AR valid, and this is the AR ready. So this is the read transaction, and then what happens? Slave will send the data. Okay, so let me write it properly. Then what will happen? Slave will send, say the burst length is 2 only, so slave will send the data. Okay, that is the R data. Then slave will make the R valid. Slave will also make the R last. Also, there will be a ready signal from the master. In addition, there will be one more signal. I can draw it here, which talks about the whether this data is correct or not. Okay, this is the additional signal. Again, it's optional, and this is nothing but the R response. Okay, so by using this R response, we'll say that whether this data is actually correct data or it's a corrupted data. Now you may wonder why I need this signal, this R response signal, when I have the R valid. So we need to understand that R valid is used to say that I have transfer the two transfer in a burst as per the request from the master, because master will tell the size of the burst, what is the transfer in the burst. So the R valid is just telling that this number of transfers are completed. But whether this data is valid or not, that can be communicated via the R response. So the proposal specifies that the required number of data transfer in a burst must be transferred. So even if the slave says that the data is an error, but since the slave has accepted the read transaction, it has to complete the read transaction. That means it has to transfer the data in a burst of the appropriate size requested by the master and appropriate transfer size. So slave cannot stop the transaction or ignore the transaction. It has to complete it. What it can do, the slave can make the error signal high, indicating to the master that I am sending you the data, but this data is corrupted. Okay. For example, if there are 8 transfers are requested from the slave, but the slave has an error condition, slave must perform the 8 data transfer, each with the error response. Okay. So this completes the discussion on the AXI memory map. If you want to test your understanding, what you can do, that you can go through this document and find out the solution to these 2 questions. Like when the reset happens on the AXI1, what is the status of the, for example, reset signal? Sorry, not reset. What is the status of the valid and the ready signal, or the, yeah, these are the ready, valid and the ready in each case, or the last signal. What is the status of this one? You can find out. Also, in case of the write transaction, we know that the master sends the address, write and control information, and then the master sends the write data. Can the master send this one first and this one? Think about it and find out the solution. Okay, so this completes our discussion on the AXI memory map. In the next couple of lectures, we'll discuss the AXI Lite and AXI Stream protocol.